So in this video and the videos to come, we'll take a look at each one of the different examples here in examples 3 through 6 to demonstrate a different algebra technique that we could make use of to try to go ahead and actually evaluate some indefinite or definite integrals. Notice here on this question in example 3, I am again focusing on an indefinite integral, so I'm just going to be looking for an answer that is a function. And the algebra technique that I'm going to make use of here is splitting fractions. Now, the reason that I know here maybe right away that I want to use an algebra technique is because certainly this gigantic horrible fraction is not any derivative rule that I have memorized. So what I'm going to go ahead and do is I'm going to start by rewriting this and then separating out my one fraction into 3 separate fractions. Remember that if I have a bunch of items being added or subtracted in the numerator of a fraction, I can very easily separate them out into distinct fractions, like I'm doing here. Notice I'm going to just take each individual term in the numerator, and I am going to make it into its own fraction with an 8 times an x to the 4th occurring in the denominator. Now, this still looks really terrible, but notice that by doing this, there's a couple other things that I might be able to start to simplify down. I can change my first term here into just 1 over 8x. I can change my second term, let's see, my x to the 4ths are going to cancel into just a 2 secant squared of x. And I can change this last term into a 1 over an x to the 4th. And now I can actually make use of a nice property of antiderivatives, specifically using my sum and difference rules in reverse. That is, I can go ahead and I can separate this now into 3 distinct antiderivatives that I'm going to be interested in finding. Now, I don't have to think about this this step, at least in this particular way. I could, if I wanted to, think about just finding the antiderivative of each piece one at a time, kind of immediately, instead of writing out each one of these separate integral symbols, but it's of course totally fine to proceed this way as well. Now I'm going to go ahead and make a couple quick modifications to this before I go ahead and actually start to find antiderivatives. First off, I'll notice that in my first integral here, there's a 1 over 8 that I could pull out of the integral. That'll make it a little bit easier to work with. Similarly, on the next one, I can go ahead and pull out the value of 2. And I notice that I'm just interested in the integral for this secant squared. I can then go ahead and go to this last integral and think about rewriting this as x to the power of negative 4. And now I can think about finding the antiderivative of each of these. So notice that in this first piece, I would end up with a 1/8 natural log of the absolute value of x. Don't forget those absolute value bars have to be there. And I'm going to have to put on a plus c. I can then go ahead and say that I'm going to have a minus a 2 tangent of x. Notice the secant squared is the result of taking the derivative of a tangent. And I'm going to have to add another c onto here. Notice that technically, since these might be different numbers, I could give these different subscripts, like maybe I call this one c number 1 and this guy over here c number 2. And then I could say that I'm going to have a minus a 1/3 x to the negative a third. Notice if I take the derivative of this, I ultimately produce this x to the negative a 4th. And of course here I could add on another c. Maybe let's call that C3. Now typically if you were to do, or if you were to kind of arrive at this step immediately from up here, and you kind of skipped the entire second line, you would see that actually, well, I would have only written, I guess, 1 plus c at the back. And that's totally fine. Essentially here I can take all of my plus c's and I could add them all together, right? If they're all individual constants and they're all added together, they just create a new individual constant. And so I could just write these kind of all at the back as just a single plus c. So again, when you're working through problems, or as we continue to work through problems like this together in this class, typically we'll be kind of jumping from a line like what we have up here almost immediately down here to the answer. And we'll tend to skip a lot of the steps that occur in between. However, it can be really useful, again, at the start to kind of write out all the steps carefully to make sure that you're processing things correctly and you are using correct algebra modifications and calculus modifications to slowly arrive at your answer. But what we've seen here in this question is that this idea of splitting fractions is a great way to take something that looks terrible and to turn it into something that resembles a bunch of derivative rules that we know how to work with.